Hello everyone, I'm Alfian and today we are going to solve the Hackerrank challenge on the problem solving section called the forming a magic square challenge. And for this particular challenge, we are using the both Java 7 and I will show you how to solve it using the TypeScript afterwards. And if you are using another programming language, then you can go ahead. And for this particular challenge, the description says we define a magic square to be n times n matrix or n by n matrix. For this case, it's 3 by 3 matrix of distinct positive integers from 1 to n with the exponent of 2 or with the power of 2. So a distinct positive integers, its range from 1 to 9, and the distinct is, in other words, is just unique number between each other, and where the sum of any row, column or a diagonal of the length n is always equal to the same number, which is the magic constant. You will be given a 3 by 3 matrix of s of integers in the inclusive range from 1 to 9. We can convert any digit a to any other digit b in the range 1 to 9 at a cost of using the math absolute a subtracted by b. So if in this notation, if we are let's say if we are returning a negative value of the difference between a and b, which is subtracted, and then the negative value will be negated back to the positive value. Let's say we have minus 2 from the difference of a. Let's say a is 3 and b is 5, and the sum of a and b, of course, it will be minus 2 or the negative 2, and then using this notation, double pipe between them, it will be converted to 2, not the minus 2. So if we are already get the number of 2 as the positive number, then we still returning a positive number of 2. And given the s of the matrix from the function right here, convert it into a magic square at minimal cost. Print this cost on a new line. And a cost in here, it means like, let's say we have the matrix like this, 5 3 4 1 5 8 and 6 4 and 2, and we can convert it into the following magic square: 8 3 4 1 5 9 6 7 and 2. And this took 3 replacements at a cost of 5 with 8, 8 with 9 and 4 with 7, which is equals to 7. The difference between 5 and 8 is 3, and the difference between 8 to 9, which is 1, 3 added by 1, which is 4, and 4 by 7 is equals to 3. Since 4 added by 3 is equals to 7, then we return the 7 as the least possible cost of converting this matrix into the proper magic square. So you might be wondering, why is it 5 with 8? We are converting the 5, which is the wrong magic square composition, into the proper magic square composition, and the cost of converting this matrix into this proper matrix of magic square, we have, let's say, for the first element of the matrix, which is 5, compared with the 8, and we got the difference between 5 to become 8, which is 3. And for the next one, since 3 and 4 is already aligned as the magic square, then we don't have to change anything, and so the cost will be 0. And also it goes the same thing with the 1 and 5. And for the 8 right here, we will convert the 8 into the 9, and then we will get a cost of 1 to convert the 8 becoming the 9 right here. For the next one, which is 6 4 and 2, and we convert 6 4 and 2 into the 6 7 and 2, which is the proper magic square. We only need to convert the 4 to the 7, that requires 3, and then we will insert the difference between 4 and 7 into our total cost right here of 7. If you're wondering what is magic square, a magic square is the square that, let's say, if we have a distinct number from 1 to 9 and it's on the 3 by 3 matrix, And the magic square of each row, if we count the row, then we will get 15. Let's say 8 with 3 is 11, and added by 4, which is 15, is the sum of all of the horizontal line that we draw on this 3 by 3 matrix. The same thing goes on the diagonal sum, which is 6 added by 5 and added by 4, and is also equals to 15. And the same thing goes to this diagonal from the top left to the bottom right. 8 added by 5 is 13, and added by 2, which is 15. And the same thing goes to the vertical or the column. 8 with 1, 9, and with 6 is equal to 15. And to visualize this, what is magic square? Let's say we have the proper magic square, which is the structure or the sequence of the magic square. 8, we have 8, 3, 4, and then using the next line, which is starting from the left, 1, 5, 9, and 6, 7, 2. And it is the same thing as I already draw right here. If we look over here, we have the horizontal line that summing the 8, 3, and 4, which is equals to 15, 1, 5, and 9, which is equals to 15, and so on and so forth. And it also applies on the vertical summing right here, and also the diagonal sum. And if you look closely, the 5 is always placed on the center of the matrix. And we have the counterpart, which is if we have 1 on the middle left, then we will have 9 on the middle right, which is the counterpart of the 1. 1 with 9 is equals to 10, and sum by 5, which is equals to 15. And also it goes the same thing from 2 to 8, and they have their own pairs. 3 with 7, 4 with 6. And from all of the numbers right here, it forms the proper magic square. So it is called a magic square. And the magic square, not just this composition of number in a matrix, but also we can rotate it, and also we can mirror it. So the possible magic square is 8. You might be wondering why is it 8? It's because from the mirror right here, we have from the first one, which is 8, 3, and 4, 1, 5, 9, and 6, 7, and 2. If we mirror to the bottom, we have this one starting from the 6, 7, 2, and also it reflects on the initial matrix right here. And also if we mirror diagonally or from this side, we got the proper mirror. 2, 9, and 4, yes, they are near each other. And also the same thing goes to the mirror to the right. And we have 4 possibilities of the magic square. And to get the rest of the 4 possibilities that I said earlier, which is 8 possibilities of magic squares, then we have to only rotate it and mirror it. So we have the 8, 1, 6, 3, 5, 7, and 4, 9, 2. And if we draw a line horizontally and vertically and also diagonally, we will still get 15. You might want to pause this video and see for yourself to check if we rotate like this. Rotating or mirroring will still resulting in every row and column is equals to 15. And let's normalize this. Let's go back to our implementation. And we need to took some kind of replacements that took only the least cost possible. And since we are working in JavaScript, then we need only to return the least cost in a form of integer right here from the function. And the name of the function is forming magic square. And in Java 7 we have the array list, a nested array list, or the 2-dimensional list of integer in a form of array list. And the parameter itself is called the s. So without further ado, let's solve this by declaring to convert the s. We need some kind of a 1-dimensional array to minimize our confusion. Let's say we have the 5. Let's say we have the array composition as like this. which is a two-dimensional array, and we need to flatten the array as 5, 3, 4, 1, 5, 8, and 6, 4 by 2. You might be wondering, why am I using the array flattening method to solve this challenge? It's because it's just to make us easier to compare against the proper magic squares available, which is we have 8 possible magic squares that we can compare it, and we can return the least cost possible of all comparison from all magic squares, all possible 8 magic squares. So and then we compare the 5, 3, 4 with the magic squares like this in a composition like this, 8, 3, 4. Let's say we already found the least cost of the magic square combination, 1, 5, 6, 1, 5, 9, sorry, and 6, 7, and 2. And since 5 is not placed in the middle, and if you notice all magic squares is in the middle of the array, and we are comparing the 5 with 8, and we get 3 as the cost, and we compare since 3, 4, 1, and 5 already match, and we need to change the 8 into the 9, which is only requires 1 cost of the conversion, and also 4 with 7, and the sum of the conversion cost, we have the least cost of 7. And to flatten our array in Java 7, it's kind of tricky. First, we need to declare our array itself called the flatten array, and we construct new integer of the number to determine the length of the new flattened array. Since the visualization already shows we have 9 lengths of the array, to get the length of the array from the two-dimensional array of the S two-dimensional array or S matrix, then we have to iterate the S matrix by declaring our integer length, which is 0, and we use the for loop to loop all of the rows of the S matrix using the for loop instead of using the normal for loop with the in I equals 0 as long as I is below the length or the size, then I++. We are using more simpler approach using the list of integer to destructure the row, which is row right here. We declare the row right here. It's declaring the 5, 3, and 4, or destructuring the 5, 3, and 4 as the row, and also 1, 5, and 8. And then from the S, as simple as that. And for the next one, we count the length using the plus equals operator, and we determine the row size. Takes only size method because we are using the array list of integer, and then we get the actual length from the two-dimensional array. And for the next one, we have to fill the one-dimensional array, copy it from the two-dimensional array right here. And to do that, we have to iterate the S matrix by using the for loop of the list integer, the row with the S, and we name it as row, from the X to destructure the one-dimensional array of each S iteration. And for the next one, we use the for loop again to destructure the row using the integer. Since inside the row is all data type of integer, then we can simply use the integer num of the individual num inside the row array, and using the row as the array from the destructured array from the S matrix. And to do that, we can assign the value to the flattened array. But before that, we need to declare our index using the index. Index is always starting from 0. And to define the first index of the flattened array, and we assign 5 into the 5 right here as the one-dimensional array or the flattened version. Instead of using the integer num is equal 0, then we need to iterate one by one in order to get the one index from the index 0, 1, 2, 3, and 4. Then we need to use the traditional for loop in I equals 0 as long as I is below the row size, then we can use the I++. We explicitly define the I as our pointer to the said index of the flattened array. Using the flattened array, we define which index that we want to assign value to. Array with the index plus plus. You might be wondering why I'm using the index plus plus right here. And after we declare index as assign the flattened array of the element of 0, then index plus plus will trigger us to the next value, assign it the index to the 1. And instead of using the for loop, the traditional for loop, then we can simply roll back to our in num on the row, iterating the every num inside the row, and then equals using the set num from the row. And we are assigning 5, our one-dimensional array right here, 5. And then for the next iteration from the row equals the 3, and we assign 3 to the index, and we add the index by 1 again to 2. And then for the index 2, we have 4 from the iteration for loop right here, and we assign 4 to already declared index right here as the 2, and then we added the index by 1 again. It's the same as using the current index like this, and then we use the index plus equals to 1 or index plus plus right here. So to sort this, I'm using the index plus plus as one line. And for the next row, from the after this for loop finishes, it iterates to the next row from the S matrix, which is 1, 5, and 8, and assign it to the row right here. And we will iterate the num from the row, which is 1, 5, and 8 into the one-dimensional array. Okay, so for the next one, we need to declare the 8 possible magic squares. Since it's only showing 1, then we declare the 8 possible magic squares by declaring a 2-dimensional array called the seed as the seeds of all possible magic squares. And to declare this, I'm using the 2-dimensional array right here and assigning another array like this, and assigning another array like this. And inside this array, we determine the one-dimensional version of the possible magic square. Since we have 8 magic squares possibility, if we look over the mirror right here, we have 8, 3, 4, 1, 5, 9, and 6, 7, 2. And we are assigning 8, 3, 4, 1, 5, 9, 6, 7, and 2, just like the proper magic square right here. And to get the rest of the magic squares possibility as the seeds right here, then we can mirror and rotate it. If we look over here, I have declared all of the combinations, all of the 8 possible combinations of the magic squares as the seeds right here. We have 8, 3, 4, 1, 5, 9, and 6, 7, 2 as the one we declared from before. And for the next one, we have 4, 3, and 8. On the second row, we have 9, 5, 1, and we have 2, 7, and 6. That is the second row of the second magic array combination. And for the third one, 6, 7, 2, 1, 5, 9, and 8, 3, 4. And also the same thing goes to the fourth one, which is 2, 7, and 6. And for the next one, how do I get the all of the 816, 3, 5, 7, and 4, 9, and 2? It's by rotating the mirror right here, and we get the same thing. If you want to pause the video, then go ahead and count from the top left to the top right, and also goes to the bottom one, starting from the left to the right, and also starting again from the left to the right. We have 8, 1, 6, 3, 5, 7, and 4, 9, and 2. And then I assign the 8, 1, 6, 3, 5, 7, and 4, 9, and 2. And that is the possible magic square right here. And let's go back to our implementation. And I already assigned the all possible magic squares as the seed by using the to save our time. Let me declare this all of the seeds possible. I'm using the Ctrl and Shift and using the arrow button to select multi-line and then pressing tab. and we fix the indentation issue. And to get out from the multi-type or the multi-cursor right here, then we can use escape button, and the more you know, the better. So to compare the least cost possible from all of the 8 seeds, then we need to compare the seeds one by one against the flattened array that we declare right here from the as matrix. Since we have, let me remind you again, since we have two-dimensional array or matrix of 5, 3, 4, 1, 5, 8, and 6, 4, and 2, then we already declare the flattened array as the one-dimensional array of 5, 3, 4, 1, 5, 8, and 6, 4, and 2. And then we compare the flattened array against all of the possible seeds and return only the least value from all of the comparison. To do that, we can use the for loop for using the one-dimensional array of the seed from the seeds two-dimensional array, and we get only one seed as our first iteration, which is the first one right here, and then for the next iteration, right, this one and also this one, comparing the seed against the flattened array by using the for loop. Since we are iterating all of the indexes from both the seed against the flattened array, then we need to use the traditional for loop of 0, 1, 2, 3, 4, 5, 6, 7, and 8, and we compare each of the indexes, and we return the sum of the cost and check if the cost is less or higher than the current one. And to do that, we can use the for loop in I is equals to 0 as long as I is below the seed dot length. Since we are using the normal integer array instead of array list, then we use the length property and I plus plus, and we iterating all of the seeds against the array, against the flattened array, and then we get the, and before that we need to get the sum of the current iteration from the seed against the flattened array. We are starting the sum from 0 using the cost or the sum. Let me use the cost instead to match the requirements right here, and we declare the cost plus equals, we iterate all of the seed elements against all of the elements inside the flattened array using the flattened array of the current index of the current iteration right here, and subtracted by the seed of the current index. And the seed right here we got from the seed as the individual seed from all of the seeds array. It's plural and this one is singular, and the seed right here, which is the singular, we are comparing the array right here against the flattened array, so we get the seed variable and using the element of the current iteration. And after we return the cost, and then we need to compare if the current cost right here is it's lower than the predefined cost. So to get the maximum possible cost in Java, then we can use the integer max value to get the max possible integer or the max positive integer into our declaration right here as the integer least cost. To get the least cost, the initial value will be maximum possible integer using the integer dot max value in num right here, and we compare the current least cost. If the least cost, or using the cost, if the current cost right here is lower than least cost right here, if the cost is lower than least cost, if it is, then we are going to assign the least cost to the new cost using the new cost right here. So to compare all of these seeds against the flattened array, and we only need to return the least cost possible from all of the possible magic squares. And then after we compare all of the magic squares, then we return the least cost possible. And for the final one, we have to return, since it's requiring the integer from our implementation right here from the function, then we need to return the integer value of the least cost. So let's run the code to see if it works. We have our output as -1 and this one is -2, and it's because we forgot the notation right here, which is using the Math.absolute to check the difference, not the negative value. If we have negative value, then for the notation right here, we return the positive value of that negative value. Like I said earlier, using the if we have -2 as our result of the cost, then we convert the -2 into the +2. To do that, we can use the math, using the math and absolute. Don't forget to wrap the flatten array of the current index and the seed of the current index, so we get the difference between the two. And we have 5 with 8, and we don't have to worry about negative number because the 5 with 8 is always equals to 3. And the absolute method, it says return the absolute value of an integer value. If the argument is not negative, then the argument is returned as non-negative. If the argument is negative, then the negation of the argument is returned. Like I said earlier, if we have -2, then we will return 2 instead. If we already returning 3, then we don't have to negate the value and we will still return 3. So let's run the code again to see if it works, and let's submit this. And we have all of the test case pass. And to solve this using the TypeScript, let me show you using the TypeScript right here. And we have the forming magic square takes the parameter, and we have the S as the two-dimensional array or the matrix of this composition, and it returns a number, the same thing just like in Java. And to solve this instead by defining the length of the newly created array with and flatten the array as one-dimensional array from the S right here, then we can simply pass in a method using the constant flatten array in the S and then flat the array like this. And for the flat method takes an argument, since we are only solving the two-dimensional array without another depth of the nested array, then we can simply ignore the parameter inside the flat method right here. Okay, so if we look over here on the flat, if we run this one, if we flat this into 2, and we will return a new instance of the array, or gets a copy of the array with the flattened value. And for this console log flat right here, for the first one on the one right here, and the flat will return as the array right here, and the 2 is flattened, but the 3, 4, 5 is not. It's in the form of array. What about using flat with the depth of 2? Of course, we are inserting 3 into the one-dimensional array, but the rest of the 4 and 5 is still not flattened. But if we add another flat to 3 to the depth of 3, then we will return all of the nested array and the nested array as the one-dimensional array right here. So since we are using the two-dimensional array and the depth only 1, so of course we are just using flat without passing any argument, and we will still return the first one right here with 1, 2, 3, and 4, and with 0 right here on the first. So let's go back to our implementation. If we look over the console.log, flatten array, and we simply return 0 as the placeholder, and let's run. And we have the flattened version of the matrix right here from the S, and we have the flattened version. So let's solve this. Since in TypeScript it's more easier by declaring our magic square seeds using the constant magic squares. You can name it as seeds or anything. It's on your preference. And we type since we are using TypeScript, then we type the two-dimensional array and equals. We are forming an array right here, and inside the array we are forming another array, so it's named as the two-dimensional array. So let's go back to from the editor right here, and since it is from the Java, then we can simply convert all of the curly brackets into the square brackets. I'm using the Ctrl D to select all of the opening curly brackets and simply type the open square brackets and deleting this part and pressing escape. And also the same thing goes to the all of the curly brackets, close curly brackets, and simply we change this to the square brackets, and we are forming a two-dimensional array of the seeds magic squares. And to declare this, we can use the let list cost just like we did earlier. Since the TypeScript is not using cannot use the Java integer dot a max value, then we can simply pass in the positive infinity to get the plus infinity, or the maximum possible integer of the list cost. And for the next one, we can simply use the for loop, or I believe in TypeScript we are using the constant num or constant seed of magic squares. Let's console.log seed to see if the array is being recorded properly. And there you have it. We have all of the seeds from the magic squares listed right here, and I'm going to change the magic squares into the seeds to match the one from the previous implementation using the Java language, constant seed of seeds. And for the next one, we can declare our let sum, or the sum, declare it by 0 to define the current cost of the both array comparison from the seed against the flattened array. To do that, we can use the let I is equals 0 in the traditional for loop. As long as I is below the seed dot length, then we can add I plus plus to the next iteration. And for the sum, we can use the plus equals addition operator and using the Math.abs just like we did in the Java, and we are going to return the seed of the current iteration subtracted by the flattened array of the current iteration. And there you have it. You have the current cost, the current sum of the current iteration of the individual seed right here. And we can add a check if the list or the sum is below the list cost. If it is, then we assign the list cost to the current sum right here, and we will return the list cost. So let's run this to see if it works, and let's submit this. Okay, so that's about it. I hope you understand my explanation. If you still don't understand, you can ask me in the comment section. I will happily answer it. Or if you have any better solutions regarding this part of a challenge, you can tell us what you think and tell us the solution in the comment section. I hope you have a great day, and I will see you in the next video. Goodbye.